Hello everyone, we're going to go ahead and get started on the fundamentals of algebra, which is section 6.6. So as an overview, we've seen arithmetic is a very valuable tool to have in our world, but working only with numbers definitely has its limitations. There are lots of things we don't know in the real world, and so a lot of the times we want to represent the things we don't know with things like variables. So in algebra, we use variables to represent quantities that change or vary, or things like unknowns. Algebra gives us the flexibility to model far more things in our changing world than fixed numbers. So variables are usually represented with letters, so that would be something like x or y in an equation. Those are what variables are. So here are basic definitions of variable, usually represented by a letter like x, is a quantity that can change. It represents the unknown values in a situation. An algebraic expression is a combination of variables, numbers, operation symbols, and grouping symbols. So an algebraic expression, this can contain any numbers. This also contains any variables like x or y. It also contains any operations, plus, minus, multiplications, division, things like that. And then we also have grouping symbols like exponents or parentheses or anything along those lines. So an expression is specific. It does not have an equal sign in it. That would be called an equation. So there's only a small difference between expressions and equations. Equations have an equal sign in it. Expressions do not. That's the main difference between the two. Algebraic expressions are made up of one or more terms, which are the pieces in an expression that are separated by addition or subtraction signs. So terms are the pieces or chunks that we kind of have that are separated by our plus or minus signs. And so, for example, on the bottom there, we see we have 3x plus 2. So one of those terms would be 3x and the other term would be 2, and they're being separated by the plus sign. Then we have 8x squared. That's one single term. There's no plus or minus sign in there, so that's just by itself. Then we have the number 111. So that's just a number. There's no plus or minus sign, so it's its own term. Then we have 9/5 c plus 32. So 9/5 c is one term and 32 is another term. And then lastly, we have 7 times 2y squared minus 5. So 2y squared is a term and 5 is a term because those are being separated by a minus sign. 7 is being multiplied, so we do have those grouping symbols there. But as far as terms go, typically we refer to those as the ones separated by pluses or minuses. So, all right, so every term has a numerical coefficient, or just what we call a coefficient. So, for example, the coefficient of negative 17y is negative 17. It's the number that's being multiplied or is in front of the other or the variable that it is next to. They're being multiplied together, and so we call that the coefficient, the number in front of the variable. Now, if it looks like your variable does not have a number in front of it, so for example, z, if you just have z, the coefficient is always going to be 1. So if it looks like there isn't a number in front of your variable, that coefficient automatically is always going to be 1. So that's always important to remember. Now, when it comes to simplifying algebraic expressions, we have a couple things we want to keep in mind. The distributive property is used very often in simplifying algebraic expressions. So for any numbers a, b, or c, we would have anything along the lines of a times b plus c is equal to a times b plus a times c. So the distributive property, we see there is a little chart there for the distributive property formula. Your distributive property allows you to take a term that's being multiplied into a, what we have if we have a sum or if we have a difference. So having A times B plus C, we distribute the A. So since A is being multiplied by the sum or difference, we can distribute that A so that it multiplies to each term within the sum or difference. So for our chart, for the distributive property formula, starting there in the upper left-hand corner, we have A times B plus C. And so we see that A is highlighted in red there, and it's got those arrows. It's being distributed to each term B and C. So when we distribute, we would get A times B plus A times C. So it distributes to each one. Then for the upper right-hand side there, we have A times B minus C. So instead of plus, so now we have a minus. It is going to work the same way though. So we'll have A times B and then minus A times C. It still distributes. And then in the lower left-hand corner there we have negative A. So now A is negative. So negative A times B plus C. So when we distribute that negative A, the negative has to follow along with it. So distributing the negative A to B plus C, we would get negative A times B. And then technically what would happen is that your plus would stay the same. You would still have plus, but then you would have negative A times C. And plus a negative turns into minus. So it would be negative AB minus AC. Then on the bottom right there, we have negative A times B minus C. So it's going to work very similarly. We have negative A times B, which creates negative AB. And then we have negative A times negative C. Now, we have negative A times negative C. In this case, that's a double negative. And so since it's a double negative, it will become positive A times C, which makes this into negative AB plus AC. So it's very important to be aware if your term that's being multiplied is negative or positive. That will make a difference when you distribute. So it's always important to keep an eye out for that. So when two terms have the same variable with the same exponent, we call those like terms. So the same variable would be the same letter. So they both, have X or they both have Y. And the exponent has to be the same as well. So that would be either, a single x or x squared or maybe y cubed. They have to match. So they have to match in both variable and exponent. Now, if they have the same variable but a different exponent, those are not like terms. X and x squared are not like terms. And then if they are not the same variable, they're also not like terms. So you can have x squared and y squared. The exponents match, but x and y don't match. So those would also not be like terms. So like terms have to have the same variable, and that variable has to have the same exponent. So you can combine any like terms only when simplifying algebraic expressions. This does work for equations as well. When you do, you simply add their coefficients together and leave the variable portion the same. So you can combine like terms together. This will be typically when you have a plus or minus in the situation. So if you are adding or subtracting like terms, you can do the operation with their coefficients and then keep that same variable and exponent on it. We'll kind of see a little bit what that looks like a little bit later. And you'll want to use a distributive property before you want to combine any like terms. So if the point of a problem is to combine your like terms, you do want to make sure that you use your distributive property, get rid of any multiplications or divisions, and so that all you're left with is going to be the sums and differences, your addition and subtraction. So if we look at the box over here to our right, we have like terms and then we have unlike terms. So we can kind of get a little bit of a hang of what the different kind of looks like. So for the like terms, we have things like 6x and negative 10x. Now the coefficient, the number in front of x, does not match, but that's okay because the only thing that has to match is the variable and the exponent. So our variable in this case is x. There is no exponent, which technically means it's an exponent of 1. So They are like terms. And we have 8x cubed and 6x cubed. They both have x, and the x has the exponent of 3. Then we have 2x squared y and negative 5x squared y. Now there are multiple variables in this case and different exponents, but we see that the term still matches. So both still have x squared and a single y. So those are like terms. Then we see 5 and 12. Well, there is no variable, and so those variables do not have exponents. Those would be combined either with addition or subtraction. Those are considered like terms. So then if we look, we can look at the unlike terms as well over there, more to the right. So we have 6x and negative 10x squared. So x is squared in this case. Well, one of the x's is just to the power of 1. So those do not match. They're not like terms. Then we have 8x cubed and then 6y cubed. So we have x cubed and y cubed in this case. Same exponent, different variables. Those are not like terms. Then we have 2x squared y and negative 5xy squared. So they both have x and y, but their exponents still don't match. So we've got an x squared in one and an x in another, and then we have y in one and y squared in another. And then lastly, we have x and 5. So x has a variable, and the exponent would be 1. And 5 does not even have a variable or an exponent to put on that variable. So those are not like terms as well. So that's the difference between like terms and unlike terms. And so we can combine any like terms with addition and subtraction when it comes to simplifying any expressions or equations. So we're going to go through an example together. We say the distance in miles a car travels is given by our formula d equals rt, where r is the rate or speed in miles and t is the time in hours. How far will a car travel in 6 hours at a rate of 55 miles per hour? So we would call d equals rt a formula. So that being a formula, it's kind of like a rule that it's telling us, it's instructions really. It's telling us that distance is equal to RT, which is going to be rate times time. That is being multiplied. And specifically, this is called the distance formula. So we want to evaluate, that's the key word here, evaluate our equation by substituting 55 in for our rate and 6 in for t, our time. So we're told that r is the rate or speed in miles and t is the time in hours. And so if it's 55 miles per hour, that is the rate, and the time is the 6 hours. So by evaluating our equation, it means we're going to replace our variables. So we're going to replace r with 55, and we're going to replace t with 6. So we would get that our formula for distance is distance equals rate times time, where we replace the rate with 55 and the time with 6. So we get distance equals 55 times 6. Distance would be 330, and in context, that is miles. So the car will travel 330 miles in 6 hours. So that's kind of an example of evaluating. So what evaluating means for these types of expressions and equations. So we plugged in the values that we had for rate and time, and so we were able to calculate the distance in that case. So all right, now we're going to do one together in our notes. We're going to simplify each of our following expressions. So this is where we're going to combine our like terms. So A is 9x minus 7y plus 18 minus 27 plus 6y minus 10x. And B is 8 times 3x squared plus 5 plus 3 times 2 minus x minus 5x squared plus x. So we're going to go ahead, we're going to simplify each of the following expressions in our notes. All right, so we have our expression here for A, 9x minus 7y plus 18 minus 27 plus 6y minus 10x. So there's quite a few things in there. we're going to go ahead and we're going to identify our like terms. So remember, our like terms are going to be any terms that have the same variable with the same exponent, and then numbers by themselves are like terms as well. So we definitely realize that in our whole expression here, there is an x, there is a y, and there are numbers by themselves. So what we're going to do is we're going to highlight our like terms so we can kind of identify which ones will be combined. So starting off just at the beginning here, we have 9x. And so we want to find something that will match our 9x there. And so we go down our list and we have, 7y, 18, negative 27, 6y, and negative 10x there. So negative 10x that will be included there. So we have our like terms, we have negative 9, or we have positive 9x and negative 10. Those are like terms. So now we can do the same thing. Now we can go on to y. So we have a negative 7y here. So we go down the list, we have 18, negative 27, and plus 6y. So plus 6y, or positive 6y, and negative 7y are like terms. Then lastly, we have 18 and negative 27. These are just numbers by themselves. That means that they are like terms. So we're going to now group all of our like terms together. If you know what to do at this point, you can skip the grouping part. But if not, then we'll go ahead and group them together. So when we say group means to put them next to each other and put parentheses around it. So we have 9x minus 10x, and we're going to write them next to each other. We can rearrange these however we want. We just want to make sure that we're keeping track of any negatives or positives or minuses and plus. So if something is being subtracted, we're going to keep that subtraction on it. So we have 9x and then we have minus 10x, so it's going to have minus 10x. And then we're going to put some parentheses. Now when we write our groups, we always want to keep our groups adding. So we're going to add our groups together. We don't want to subtract our groups. And so now we'll go on to the y group. So we have negative 7y plus 6y, and there's a group there. Then we'll add our last group here, which were our numbers 18 minus 27. And so now what we're going to do is we're going to simplify each of our groups. They are like terms. We can now add or subtract them together. So that's what we're going to do. So we have our coefficients, and remember when we combine our like terms, we're really paying attention to our coefficients here. So we have 9 minus 10, and they both have x on it. And so 9 minus 10, if we just think of the coefficients, that would end up being negative 1. Well, they both have x, so x sticks around for the ride. So we're combining these terms really just by combining our coefficients, and they're going to keep the same variable with the exponent, the same like term. So now we'll go on to our y terms. So we have negative 7 and positive 6. So when we have negative 7 plus 6, that's going to end up being negative 1. And they both have y, so the y sticks around, so it'll be negative 1y. And then lastly, we have our two just single, individual number terms. So 18 minus 27, we can just calculate that out. It's going to be negative 9. All right, so we're just about done here, and you could certainly leave your answer this way, but what we typically do is that we typically don't write one variable like 1x or 1y. And it's kind of the same thing with negative. So negative 1x, negative 1y. We typically will just drop the 1 and just keep the negative. So instead of saying negative 1x, more often we're going to say negative x. And we'll write this all in one color here. So negative x. And then we have plus negative y. Plus a negative is the same as minus. So we have negative x minus y plus negative 9. Once again, just write that as minus 9 instead. And that would be our expression in its most simplified form. And there we go. Negative x minus y minus 9. So let's go ahead and go on to part B. Part B here is trickier because now we have coefficients in front of whole terms here. So we will need to use our distributive property. So we're going to go ahead, we'll use our distributive property here. And we're going to distribute, we're going to start with the 8. So we're going to multiply 3x squared and 5 by 8. So when we multiply these together, you can either just take this in one single step or you can write it out like how we're about to. So we have 8 times 3x squared plus 8 times 5. So we distributed that 8 to be multiplied into each term. Then for our second part here, 3 times 2 minus x, we're going to do the same thing. So we're going to have 3 times 2 and 3 times negative x. So we're going to keep adding here, because remember we always want to add our groups together. So we'll have 3 times 2. And then that inner part there, that was 2 minus x. Minus is the same as plus negative. So we can really just change this into 3 times negative x. And we're adding our groups. So 3 times negative x. And then lastly, we have a little bit of an interesting part here. So we have a group at the end. There's no number, but it is being subtracted. So that subtraction, like we said earlier, we said that if a variable didn't look like it had a number in front of it, technically that's 1. And that's really the same thing that's going on here. It doesn't look like there's a number in front of our group, 5x squared plus x. So really it means 1. And it's a minus 1, which is really the same as plus negative. So the coefficient of our group, 5x squared plus x, is really negative 1. So we're going to distribute our negative 1 into our group. So we'll have plus negative 1 times 5x squared plus negative 1 times x. So using our distributive property, we got all of our different terms all written out here and expanded out. So now we're going to simplify these terms. So 8 times 3 is 24. So we have 24x squared. 8 times 5 is 40. 3 times 2 is 6. 3 times negative x would just make negative 3x. So since we have a negative x, that's really like a negative 1x, and 3 times negative 1 is negative 3. So we have plus negative 3x. If you'd like, to make it more comfortable, you can put parentheses around it just to make very clear that this is a negative number. Then we have plus negative 1 times 5x squared. Negative 1 times 5 is negative 5x squared. I like to put parentheses around my negative numbers just to keep it very clear what's going on. Then lastly, we have negative 1 times x. The coefficient of x, remember, is 1, so negative 1 times 1 is negative 1. So to make it negative, remember, we don't really write negative 1x, we just write negative x. So now all of our terms are simplified. We still have parentheses around our negative numbers there just to make it clear that they are negative. So now that we've distributed and kind of simplified a little bit, we can now focus on combining like terms. So starting in the front with 24x squared, we'll try to see if there's any like terms. And you could very well not have any like terms in a expression that you have. It is completely possible to not have any like terms, which in that case it would just stay the same. But so we have 24x squared, and we're going to go down the row. We have 40 and 6. Negative 3x is not a like term. It does not have the exponent of 2. But negative 5x squared is a like term. And then lastly, we have negative x. Does not have the exponent of 2, so that is not a like term. Then moving on to our next number here, we have 40. So 40 is by itself. There's no variable on it, so no variable, no exponent. So it's just a plain number. And the next one is also a plain number, so those will be like terms, 40 and 6. Then lastly here, we go on to negative 3x. So negative 3x, it has an x with no exponent, really meaning exponent of 1. So negative 3x. The only other option here is negative x, and yes, they are like terms. They both have x with no exponent, which means exponent of 1. So those are all of our like terms, so we are now going to combine them. So just like before, we are going to group them together. So starting with 24x squared plus, and we have negative 5x squared. So that is grouped together. We have plus our next group. Now, typically when we put these groups, we typically go in decreasing exponential order. So x squared starts, then we would have x, and then we would have our plain numbers at the end. That is typically how we format it. Although if you don't format it exactly the same, it is still correct. It's just not typical. That's kind of the difference. So we're going to write our x terms next. So that is negative 3x plus negative x. Then lastly, we have our numbers just by themselves. We have 40 and 6. So now we're going to combine as well as we can. So 24x squared plus negative 5x squared. So we're going to add the coefficients. 24 plus negative 5 is going to end up being 19x squared. Then we have negative 3x plus negative x. So negative x is like saying negative 1x. So negative 3 plus negative 1 is negative 4x. And then our last group there, 40 plus 6 makes 46. Now we're just going to change any last things here. We do see that we have a negative 4x, and that is being added, so plus a negative is the same as minus. So we're going to rewrite this final answer here as 19x squared minus 4x plus 46. And that would be our final answer there, our simplified expression with distributive property and combining our like terms. So let's go ahead and go on over back to our lecture. So now we're going to do another example together. We have, while shopping at her favorite department store, Carmen found a dress that she's been hoping to buy on the 40% off clearance rack. For A, we are going to write an algebraic expression representing the new price of the dress before tax And then we're going to write one for the total price including tax. We're going to use 6% as the sales tax rate to do this. Then for B, we want to know if the original price of the dress was $59, find the discounted price and the total amount that Carmen would pay including tax. So there's kind of a lot of things going on here. It's on the clearance rack. We know it's 40% off. So the price of this dress is going to have that 40% off. And so we'll have to find an expression that represents that 40% off portion. And then we're going to need to write another expression that also includes the addition of sales tax. And your sales tax, which is 6%, will go onto the price of the discounted dress. So we'll use the expression of the discounted dress and take 6% of that and have to add that on because tax is added onto a price of an item. Then once we've done that, then for B, we will use the price of $59 to actually calculate the value of the dress that Carmen buys. So let's go ahead and do this together in our notes. All right, so doing these problems, the wording is going to be very important. So we want to kind of highlight some of this wording here. We're saying that at her favorite department store, Carmen found a dress that she's been hoping to buy on the 40% off clearance rack. So the words 40% off, if you've ever shopped before, hopefully you do slightly understand this meaning. 40% off is going to be 40% of the price is taken away, or it is 40% less. So 40% off is the same as 40% less than original. And the word less will indicate a subtraction here. So less indicates a form of subtraction. So we're going to have some sort of subtraction in our expression. So the first thing we're going to do is we're going to get the new dress price. And this is going to be before the tax. So the new dress price, so we're having 40% off, 40% less than the original. So whenever we work with math, whenever we have percentages, which we do talk about very often, percentage gets turned into decimal. So 40% is the same as 0.4 in decimal in that case. 40 is the percentage. You would take the decimal place 40.0 and you move the decimal place 2 spots to the left. So moving that 2 spots to the left would give us 0.4. So our new dress price is going to include 0.4 of whatever that dress price is. So to help us out, we're going to verify, or we're going to define a variable. We're going to say D is the cost of the dress. And that's the cost of the dress originally. And we're going to give ourselves a teeny bit, we're going to give ourselves a teeny bit more room here by moving this. So for our new dress price, it's 40% off. So we want to know what is 40% of our original cost of the dress. So when we talk about 40% of, or a percentage of, that word of indicates multiplication, as we've gone over in the past. So 40% of something, which is now going to be used as decimal, 0.4 of multiplication is 0.4 times cost of the dress. So that gives us our 40% portion. So we would have 0.4 times D. That's the 40%. So we'll label that. That's 40% of cost of dress. Now, a lot of the times we'll do this and be thinking that we're done. That is 40% of the cost of the dress. But remember, it's 40% off. So it's the original price of the dress minus that new value. So the original price of the dress minus 40% of that cost. That would make it 40% off to include that subtraction value of the off portion. So our new dress price would be the original price minus 40% of the cost. Now, in addition, you could have in the beginning, if you knew it was 40% less than the original, that really means that there is 60% left. This is actually the same formula as 0.6 times D. We're not going to use that, but it is the same thing. So if you did think of that at some point, then that is great. If not, then this is how we're going to do it. So we're finding that 40%, and then we're subtracting it from the cost of the dress. So that's going to be our equation there for the new dress price. So now we need to calculate the new price after tax. So we have new price, new dress price. After tax. All right, so our new dress price after tax is going to be the discounted price of the dress. And we can just write this out. Write this out in our notes. Come on, there we go. Discount price, and then it's going to be plus tax. So it's the discount price plus tax. Well, this is the discount price. That is your dress price before tax. So your discount price is that equation. So that's what's going to replace this portion here. So discount price is D minus 0.4D. So that is the discount price. But now we're adding tax onto this. So when we're adding tax onto this, our tax is taxing the price of the dress, which is our discounted price. And it's 6% is the sales tax rate. So we're taking 6% of our discount price, and that is being added. So there's quite some things going on here, but we're adding our tax amount. Our tax amount is 6% of the discount price. Now remember, this is the discount price. So if we are saying that our tax is 6% of the discount price, remember, of means multiplication. 6% in decimal is really 0.06. So really we're going to have 0.06 times the discount price, which is the entire equation of D minus 0.4D. So our new dress price is the discounted price from our dress before tax plus 6% of that cost for our sales tax. So we created two separate equations here, a before tax price and an after tax price for our dress. And so we kind of talked that through a little bit to kind of identify, what portions were what. So remember, this was discount price plus tax on discount price. These were our answers for this portion, so we'll highlight these. And then for our second part, for part B, we want to know if the original price of the dress was $59. We want to find the discount price and the total amount that she's going to pay, including the tax. So all we're going to do is plug in 59 for the price of the dress for D into both of these equations to get our new price. So let's go ahead and do that. So the new dress price before tax, like we said, was going to be D minus 0.4D. So since we're saying that D is 59, we'll have 59 minus 0.4 times 59. So we can put this in our calculators if we want, but 59 minus 0.4 times 59 is going to give us 35.4. Now we are talking about money, so this is $35, and instead of saying 0.4, remember we're talking about cents, that's always going to be 2 decimal places, so it'd be 0.40 instead. So our discounted price for the dress would end up being $35.40. Now our new dress price after tax this was our longer equation. This was D minus 0.4D plus 0.06 times D minus 0.4D. We're going to plug 59 into this equation. So we'll have 59 minus 0.4 times 59 plus 0.06 times 59 minus 0.4 times 59. Now we do know what the value of D minus 0.4D is, or 59 minus 0.4 times 59 is. So you can input that. You can make it a little easier on yourself. 35.40 plus 0.06 times 35.40. And so we can use a calculator to do this one, and this would end up giving us 37.52. We always, even if we need to, we should round to have 2 decimal places. So if you don't quite have 2 decimal places, then you'll add zeros to get to 2 decimal places. If you have more than 2 decimal places, you will round to 2 decimal places. And then once again, this was in dollars. So the price of the dress, including tax, would be $37.52. So, all right, we went ahead and finished that one up. So let's go on back to the lecture. And that wraps up section 6.6. So in 6.6, we learned how to identify terms and coefficients, simplify and evaluate algebraic expressions, and apply evaluating expressions in our world. So, all right, that was section 6.6, and I'll see you in the next one.